Space is a vast and empty place, or so it seems. We often imagine it as a silent, unchanging vacuum where everything moves along predictable paths, governed only by the immense pull of gravity. Planets orbit stars, and moons orbit planets, all in a grand cosmic dance choreographed by Isaac Newton's laws. For centuries we thought this was the whole story, but what if there's another force at play? A force so subtle, so gentle, that for the longest time we didn't even know it was there. A force that can change the destiny of entire worlds. This hidden force isn't a mysterious new kind of gravity, nor is it some exotic energy from a distant galaxy. It's something much closer to home, something we experience every single day. It's sunlight. That might sound absurd. How could the gentle warmth of the sun possibly move a mountain-sized rock hurtling through the cold emptiness of space? An asteroid can weigh millions of tons, a colossal chunk of stone and metal. Yet this is exactly what happens. The story of how we discovered this incredible phenomenon is a journey into the heart of physics, a testament to human curiosity. Our story begins in the mind of Ivan Osipovich Yarkovsky, born in 1844 in the Russian Empire. He wasn't an astronomer peering through giant telescopes. He was a civil engineer working for the Russian railway system. His world was one of steam engines, steel bridges, and the practical challenges of building infrastructure across a vast and unforgiving landscape. He spent his days thinking about thermodynamics, heat transfer, and how materials behave under stress. Around 1900, Yarkovsky self-published a small pamphlet laying out his incredible theory. He imagined a small, dark object spinning in space, illuminated by the sun, and applied his engineering knowledge of thermodynamics to this cosmic scenario. He reasoned that as the asteroid spins, the side facing the sun would heat up. But because of thermal lag, the hottest point wouldn't be at midday, but in the afternoon part of the asteroid, just like the warmest part of our day on Earth. As this superheated patch rotates into the cold of night, it radiates its heat away into space. This escaping heat would act like a tiny, continuous rocket engine, giving the asteroid a gentle but relentless push. This was the core of his genius. Over millions of years, this thermal force could cause asteroids to spiral slowly inward toward the sun, or drift outward into the colder reaches of the solar system. To understand the Yarkovsky effect, we need to zoom in to the scale of individual particles of light. Sunlight is actually a constant stream of tiny energy packets called photons. While a photon has no mass, it does have momentum. When a photon strikes the surface of an asteroid, it transfers a minuscule amount of its momentum to that object. In the vacuum of space, these tiny pushes can really add up over time. The real magic begins when the asteroid's surface absorbs the sunlight and gets warmer. As it cools down, it releases that stored energy as heat or infrared radiation. These outgoing thermal photons also carry momentum, giving the asteroid another tiny push in the opposite direction. The direction of this thermal push depends entirely on how the asteroid is spinning. An asteroid with prograde rotation gets pushed forward in its orbit, slowly spiraling outward. One with retrograde spin gets pushed backward, spiraling inward toward the sun. So the spin of an asteroid becomes its destiny. Two identical asteroids can have completely different futures based simply on which way they are spinning. The spin is the switch that determines the direction of the Yarkovsky effect. For decades, the Yarkovsky effect was a brilliant but unproven theory. That changed in the early 2000s with asteroid 6489 Golevka. This half-kilometer wide rock became the first object where the Yarkovsky effect was directly measured. Scientists used powerful radio telescopes to bounce radar signals off Golevka's surface, measuring its position with pinpoint accuracy over more than a decade. When they tried to predict its future path using only gravity, they found a problem. Golevka had drifted 15 kilometers from where gravity alone said it should be. When scientists added the tiny thermal push to their models, the predicted path snapped into place, perfectly matching the observed drift. They had found the missing piece. The asteroid Bennu has given us the most detailed look at how the Yarkovsky effect works. NASA's OSIRIS-REx mission spent years orbiting this dark, carbon-rich asteroid, measuring its drift of 284 meters per year toward the sun. This measurement is profoundly important for Earth's safety. Bennu is classified as potentially hazardous, with a small chance of impacting Earth in the late 22nd century. To predict its future path accurately, we must account for the Yarkovsky effect. OSIRIS-REx didn't just observe, it collected samples of Bennu's surface material. By studying this sample in our labs, scientists can further refine our understanding of how sunlight interacts with these bodies. Why does all this matter? The answer is simple and deeply personal: survival. The Yarkovsky effect isn't just scientific curiosity, it's a critical factor in planetary defense. We live in a cosmic shooting gallery, while a civilization-ending impact is extremely rare. Smaller impacts that could destroy a city are statistically inevitable over long timescales. Our best defense is knowledge, finding potentially hazardous asteroids and predicting their paths with incredible accuracy. If an asteroid is nudged by just a few hundred meters every year, over 150 years, that adds up to tens of thousands of kilometers. This accumulation can be the difference between a safe flyby and a direct hit. Understanding this effect opens exciting possibilities. Instead of dramatic Hollywood-style missions with explosions, we could use the asteroid's own physics against it. A robotic mission could simply paint one side of an asteroid, turning the natural thermal push into a controlled thruster. The same force could transform asteroids from threats into opportunities. By carefully altering asteroid surfaces, we could guide valuable resources from the asteroid belt into useful orbits, using the free energy of the sun to move entire mountains across the solar system. This principle extends far beyond our solar system. Every star bathes its planetary systems in light, meaning similar forces are likely at work throughout the universe. The Yarkovsky effect is probably a universal phenomenon, a standard piece of the cosmic toolkit for building planetary systems. The story of the Yarkovsky effect showcases our incredible ingenuity, developing technology to measure a force so faint it can barely be detected, yet so important it could determine our planet's future. We are the first generation who can both understand and potentially act on this knowledge. So the next time you feel the warmth of the sun on your face, remember that you are experiencing the same energy that is, at this very moment, moving mountains in the cold darkness of space. You are connected to a cosmic process that has been shaping our solar system for billions of years. The story of the Yarkovsky effect is a story of human curiosity, of our relentless quest to understand the world around us, and of the simple, elegant, and often surprising ways that the universe works. From a forgotten railway engineer's pamphlet to cutting-edge planetary defense, sunlight's gentle nudge continues to reshape our cosmic neighborhood, one asteroid at a time.